So hey, I'm Spider-Man, and in this video I will be solving calorimetry calculation problems. I recommend watching the videos of Introduction to Thermochem and Introduction to Calorimetry, which are posted on this channel, because I explain the relationship between system and surroundings, enthalpy change, and I also speak on these different variables and equations and used in calorimetry and what they represent. So I also speak about what system and surrounding is specifically in a calorimeter, and this information is important because it helps you get a better understanding of these questions and how to solve them. So on to the first question. Based on this chemical reaction, it looks like NaCl is dissociating in water into ions, and the enthalpy change of the reaction is positive. That means the enthalpy of the reaction is also positive, and the Q reaction is also positive. So if 37 grams of NaCl is added to 1.25 liters of water at 25 degrees Celsius, calculate the final temperature of the water. So also in calorimetry problems, the water or the calorimeter is considered the surrounding, and the thing that's reacting in the water, or the thing that's dissolved in the water, is considered the system. So let's see what we've given so far. We've given the mass of the NaCl, which is 37 grams. We know the volume of the water. Now in water, right, it has a specific property that 1 liter of water is equal to 1 kilogram. So 1.25 liters of water would be equal to 1,250 grams. We need grams. When we're looking at mass, we need mass in grams. So this is important to know. So mass of water is equal to 1,250 grams. H2O. And this is this. So we also know the initial temperature of water. So T initial is equal to 25 degrees Celsius. But I'm just going to make this clear. So H2O mass is equal to 1,250 grams. So we need to calculate the T final, right? Now we need to use these equations to solve this problem. So we can see that temperature is only located in the Q surrounding equation, where Q surrounding is equal to mass times specific heat capacity times delta T, which is a change in temperature. So we need to get to this equation and isolate for delta T, and then find the final temperature. Quick note that delta T is equal to T final minus T initial. So now that we have this in mind, let's solve. So we need to get to Q surroundings. We don't have Q surroundings, but we do have mass, and we have the enthalpy of the reaction. With this information, with mass, we can calculate the amount of moles by using molar mass, and then we can sub into this equation to isolate for Q reaction. Q reaction will then allow us to find the Q surroundings, and then it will help us to isolate for delta T in this equation right here. So let's do that. So the moles is equal, let's use this formula, moles equals mass over molar mass. Mass over molar mass. So we need to calculate the molar mass, but to save time, the molar mass of NaCl is 58.4 grams per mole. So let's plug it in. So we know the mass is 37.0 grams, and the molar mass is equal to 58.4 grams per mole. Grams cancel out, leaving moles. So N equals 37.0 divided by 58.4 is 0.63259 moles. Now we know the number of moles. With this information, we can find Q reaction by isolating for Q reaction. So the isolated version of the formula is this: Q reaction is equal to H reaction times the number of moles. The H reaction is this: 3.9 kilojoules. We will convert it to joules. 3,900 joules times 0.63259 moles. And this gives us 2,467 joules. Now, with this information, we can calculate the Q of the surroundings. The Q of the surroundings is the negative of this number. So, Q surroundings equals to negative of 2467 joules. So Q surrounding is equal to negative 2467 joules. With that information, we can plug all our values into this formula and then isolate for delta T. So delta T is equal to Q surroundings divided by mass times specific heat capacity. To Q surroundings divided by mass and specific heat capacity. So the specific heat capacity we are not given, but it is known that the specific heat capacity of water is 4.184 joules over kilograms times degrees Celsius. So delta T is equals to Q surroundings, which is negative 2,467 joules over the mass of the water, which is equal to 1,250 grams. Grams. The specific heat capacity, which is 4.184 joules over grams times degrees Celsius. And this gives us negative 0. Cancel the joules, cancel the grams, and we're left with degrees Celsius. And the change in temperature is equal to negative 0.4717 degrees Celsius. This is the change in temperature, so let's calculate the final temperature. The TF minus T initial. And so since we know this, the T final minus T initial, we know that T final minus T initial is equal to, so we know T final minus T initial equals negative 4717 degrees Celsius. Sorry, negative 0.4717 degrees Celsius. We know T initial up here. T initial is given at 25 degrees Celsius. With this in mind, we just plug in the values we know. So TF minus 25 degrees Celsius equals negative 0.4717 degrees Celsius. TF is equal to negative 0.4717 degrees Celsius plus 25 degrees Celsius. And the answer is around 24.5 degrees Celsius of the final temperature of the water. So let's write a therefore statement. Therefore, the final temperature of is 24 degrees Celsius. In this question, nicotine burns according to this equation given. And so a 650 milliliter sample of water initially at 23.17 degrees Celsius was heated to 93.52 degrees Celsius inside an aluminum calorimeter. The mass of the aluminum calorimeter is given, and when a 7.35 grams sample of pure nicotine was burned completely, calculate the change in enthalpy for the combustion of nicotine. So the specific heat capacity of the aluminum calorimeter is 0.90 joules over kilograms times degrees Celsius. So this is a different question in the sense that it is an exothermic reaction, and since it's burning, right, the nicotine is actually releasing energy to the water and to the calorimeter. Let me draw a diagram to explain what is happening. So this is the aluminum calorimeter, right? This is the water inside the thing. And this is the nicotine. The nicotine is burning and it is releasing energy to the aluminum calorimeter into the water. So the H of the nicotine would be a negative number, the delta H, the enthalpy, the change in enthalpy. So let's see what is given. So we know, so see, the temperature of the water and the calorimeter would be changing the same. It changes from 23.17 degrees Celsius to 93.52 degrees Celsius because the water is inside the aluminum calorimeter. So with that in mind, let's see what's given. So we are given the 650 milliliter sample of water. So we talked about how a property of water is 1 gram of water is equal to 1 milliliter of water. So 650 milliliters of water would give us the mass of 650 grams. Then we know initially at 23.17. Okay. we know the specific heat capacity of water is also 4.184 joules over grams times degrees Celsius. For the aluminum cal, the mass is given as 1.25 kg, which is 1,250 grams. 50 grams. The specific heat capacity of the aluminum calorimeter is 0.908 joules over kilograms degrees Celsius. 0.908 joules over kilograms degrees Celsius. And the change in temperature for both is the same. Change in temperature would be equal to 70.35 degrees Celsius. Also, we're given one more thing, which is the mass of the nicotine, which is 7.35 grams. So, 5 grams. So now, with this information in mind, let's calculate the Q for the water. So the actual Q surroundings consist of both the water and the aluminum calorimeter, and since that, the Q of the surroundings would equal to the Q of the water plus the Q of the calorimeter. So let's do the Q of the water. Water first, which is equal to mass times specific heat capacity times delta T. The mass is equal to 650 grams times 4.184 joules over grams degrees Celsius times change in temperature is 70.35 degrees Celsius. This gives us 191. This gives us 191,323.86 joules. The Q of the calorimeter is equal to 1 grams times specific heat capacity, which we're given, which is 0.908 joules over kilograms degrees Celsius. 908 grams times degrees Celsius. Okay, grams times degrees Celsius, and times the change in temperature, which is the same for the water and the calorimeter, which is 70.35 degrees Celsius. So this will give us 79847.25 joules. So the Q cal, the Q surroundings would equal the Q cal plus the Q of the water, which would give us around 271,171 joules. And with this, we can use this formula right here to find the H of the reaction. First, let's find the Q reaction. Q reaction is equal to negative Q surrounding. So Q reaction is equal to negative 271,171 joules. The moles of the nicotine is equal to mass over molar mass. So you can calculate the molar mass of nicotine, but just to save time, I have it in hand. So the mass is 7.35 grams over 162 grams over moles, and this is equal to 0.04537 moles. Since you know the moles of nicotine, you can use this to solve for H reaction, delta H reaction, which equals to Q reaction over moles. Q reaction is equal to negative 271,171 joules over 0.04537 moles. H reaction is equal to, this will be a big number in joules, so I'll just convert it to kilojoules, which would give me negative 5 97.8 kilojoules over moles. Now, with this in mind, we have our final answer. So the enthalpy, we've calculated the enthalpy of the combustion reaction. We calculated the enthalpy change for the combustion of nicotine. So therefore, the enthalpy change for nic is equal to negative 597.8 kilojoules over moles. Thank you for watching. This concludes the video.